So, good morning everybody, and thank you for having come here despite the holiday yesterday. And the subject of today and probably most of next week will be the structured proof language ESA. So we will move beyond this apply style and write proofs that are really more readable than what we've done so far. Nice. So we will start today by giving you an example-based introduction to the proof language. So not an abstract definition of it, but just loads of examples. And then I will show you a collection of proof patterns that cover particular situations like case distinctions and what to do with quantifiers. And then, if we have time for it, I may already get on to the subject of streamlining proofs in the sense of making them more concise and using additional features that I haven't introduced yet. And then next time we will go on to proof by induction. So these apply scripts are all very well, but they are unreadable for anybody except for the person who runs them. They're hard to maintain. If you have a long apply script and you change something in the system or you change something in the statement, the proof will break somewhere and it's very difficult to figure out what exactly happens. And they just do not scale. If you have long and complicated proofs, it's terrible to do that in an apply style. It's like the problem is it doesn't have any structure, and it's really like an assembly language program, and people don't like assembly language programs much either. And so what we'll move now on to is something called ESA, which stands for Intelligible Structured Automated Reasoning. And you can think of them as structured programs with assertions. Of course, structured programs with nested blocks and so on are nice already, but they can be unreadable too because they don't tell you if you're at a certain point what are the values of the variables, what are the invariants, whatever. And so without giving that additional information, structured programs are not that easy to read either. So this is why these ESA proofs contain a lot more information. They contain many formulas that show you what am I currently trying to prove, which is completely absent from an apply script. There you just have the commands, but what is being proved is implicit. But it's still useful to have these apply scripts to explore your proof and figure out what approach you should be using, so you don't completely forget about it. So this is what a typical ESA proof looks like. It's a block structured thing, and it's enclosed in proof and QED, and in between you have a sequence of steps, and typically you start with some assumptions that you make, and then you have some intermediate steps here that use the keyword have, and then you have a final result of your block. That's what the show is. And all the intermediate halves are not part of what is being proved. What is being proved is really just the implication from that first assumption, or assumptions, in case there are multiple ones, to that last show. That implication is the result of that block, provided, of course, the proof checks. So if it's about complaints that some step doesn't work, then you don't get any result out of that block. And the individual proofs, they may be proved by the standard proof method that you already know, sim, blast, or whatever. Or, of course, each of these bys here may again unfold into a structured object with a proof at QED. So that depends. Here, we just, for simplicity, I assume that all the proofs are atomic ones. So, does that make sense so far? Then let's really look at the syntax, the core syntax. There's a lot more, but this is what we will initially start with. So what is a proof in that language? It's either a structured object with a begin and an end, namely proof and a QED, and then optionally, so these square brackets around the method mean are not part of the concrete syntax, but about the part of the meta language, and it means this method here is optional. So you could just write proof, but you could also write proof followed by a method, and that means please prove whatever you're supposed to prove at that point using this proof method here. So a typical case where the proof method is explicit is if you say proof by induction. In fact, you wouldn't say by induction, you would just say proof, and then here after the proof keyword, induction on some variable. And then follow a sequence of steps. So this is what you see here. There you have a sequence of steps, assume, have, and show. And then it's closed by a QED. Or the proof can be an atomic thing where you just say by and then some proof method. And the proof methods are the ones that we have already seen, simp, blast, induction, or whatever. And what is a step? There are, in this basic subset that I'm introducing, there are 3 kinds of steps. The first one is just something that we'll come to later, introducing a local variable. That's the fixed variable, and that corresponds to the big universal quantifier that we've seen so far that always is in front of each subgoal. And then we can assume something, assume some proposition, and that corresponds to an implication, or rather to the left-hand side of the implication. You assume the left-hand side of the implication, and at the end of the proof block, you'll show the right side of the implication. And then come the actual proof steps where something happens. Here, have or show, that's again meta syntax, the parentheses and the or here. So you can, this step here is either a have step or a show step, and it has a proposition that's being proved, and it has a proof using the syntax up there, how it's being proved. And optionally, you can also say, oh, please use the following facts. So fact will come in a moment, and the plus means it's a sequence of facts. So you can explicitly say, use the following facts in this proof step here. So you're piping in a Unix-like fashion certain facts into the proof step. And what happens to those facts, that is what the proof that you're giving here will look at those facts, and depending on what the proof step is, it'll do something suitable with the facts. So what is a proposition? A proposition is just a formula, but it can optionally have a name. So that's very important because now we will be able to name things, and we will be able to refer to intermediate results by their name. And what is a fact? Well, in the simplest case, the fact is just a name, and you're referring either to some global lemma that already was proved earlier when you say from fact, or you're referring to something that was proved, not again, that was proved earlier, was proved further up in the proof block. So what do we do now? Brilliant. I could fix it myself. Last time I had to call some technician. I just wish it wouldn't do that. It's good. Better for contrast. So, back to the slides. So this is the main grammar. Proofs, atomic or structured objects, methods. Proof methods are what we know. Steps can be introducing a local variable, assuming a proposition, or actually proving either an intermediate statement with have, or proving the final statement with show. And propositions are just formulas, optionally named, and facts here from fact are just references to something you have already proved. So let's go through a number of examples to see this language in action. So the first, we introduced the language with variations on a proof of Cantor's theorem. Never mind if you know this theorem, that's not the point. The point is really introducing the proof language to you. So what am I trying to prove here? That a function f, which I have constrained to be of type A to A set, so from a type to its power set type, that function cannot be surjective. Or, as Cantor put it, there is no surjective function from a set to its power set. So this is what we're trying to prove. And we start just by proof. So this is an example where I don't explicitly tell the system how to prove it, but the system will do some default, will apply some default proof method at that point, if I don't say what it should be doing. And the default proof method will be selected based on the form of the formula, and in particular, if you're trying to prove a negated formula, the system will automatically say, oh, if you're trying to prove something negated, then we will assume the unnegated formula and try to derive a contradiction from it. So that means the default method here is that you are now allowed to assume that the function is surjective, and you have to show that that false follows from that. So now we explicitly state f is surjective, so we are allowed to do that, but you still have to write it down. So this is the difference between what we've seen so far, where you apply some proof method and then you just say, give the proof method, but you don't show the reader what the effect of that proof method is. And here you say, okay, we assume that f is surjective, and then later on in the text, at somewhere further down, we will show false from that. And we give the assumption a name, we call it little a. And then we proceed from that to derive the contradiction. Okay, so first let's just basically unfold the definition of what surjective means. So from that assumption A, we have an intermediate formula B, namely that for all sets A, there exists a little a, such that this big set A is the image of little a under F. That's just another way of expressing that F is surjective. Everything in its range is actually can be obtained as the image of some element of A. So I've left out the types here, that A is a set and little a is of type A, because that is implicit from the fact that one is the result and the other is the argument of F. And this you can just prove by simp using the definition of surjectivity. So that's unsurprising. So now the next step may be a bit more surprising, namely, hang on, this is again not surprising. Yeah. So from that statement B that we've just proved, I get a statement C, namely that there should be a little a such that this funny set here is the image of little a under f. Why can I prove that? Well, this statement here is simply a specialization of the statement above. The statement above says for any set capital A, the little a exists. Now here I'm saying, well, then it has to exist in particular for this funny set here, the set of all x, such that x is not an element of f of x. And therefore, the step from B to C is just a step in pure logic and set theory. So all you need to do is bypass. There's really, in fact, you just peeled off that universal quantifier and instantiated the A, the capital A, with a set of all x such that x is not in f of x. So that much is also unsurprising, but now what may not be immediately obvious is that this is contradictory. So this statement here, that there is a little a with this property, is contradictory, and we can show false by blast. If you don't see it, it doesn't matter at all, because we're not interested in the proof itself, we're interested in the structure of the proof. So just believe me, this is, the false is an easy logical consequence of that statement C, and we will actually go through the details. We will go through the how you get false from statement C in more detail a little bit later. But now you have derived the contradiction that you wanted to derive or that you had to derive, and then you can close your proof with QED. Question about that? What's going on here? Well, then let's look at this proof in the actual system, and let's look at some modifications of this proof that make it less verbose, because this is quite a verbose proof. Lots of names have been introduced, and part of the art of writing a readable proof is that you get rid of as many names as possible, because names always mean cross-references, and then you have to jump all over the proof and to see what the name refers to, and it would be nice to avoid that. Was not it? Try again. Yes, this is it. So here is our example, and here you simply see what you just saw on the slides, except that I have I've used as labels digits rather than ABC. Digits are acceptable, but you can't do any basic programming here and start with 11, 12, 13, 15, so on. You really have to stick to digits, so the system tries to enforce that you don't do any spaghetti proofs, which are completely difficult to read. But what you can see very well from this layout is that in this case, we are following a particular layout, namely it's always from the previous statement, whether it's an assumption or something that you've just proved, you get the next statement. So it's like a cascade, or it's in some sense like a Unix pipe, that you pipe something into the process and the result goes into the next step. And that's of course a very nice situation, because then you can actually dispense with the names. You can always just say, oh, from what we've just proved, now the next thing follows. And we don't need to invent these names. And this is what you see. This is not quite what you see yet. Here in the somewhat shorter proof that you see down here, I'm still using these names, but I have collapsed two steps into one. So the step 1 and 2 have been collapsed, simply so that the proof becomes a bit shorter. And when I keep on manipulating it, I'm manipulating a shorter proof. So it's basically the same proof. I'm just doing two things. I'm just doing these two lines in one line. So this by-auto does the two steps in one. And now we will get rid of the labels. So if you now compare this proof up here with the proof down here, you see the names have gone, and instead I'm saying from this So this always refers to what you have just either assumed or proved, and therefore we don't need to give it a name. Otherwise, it's really the same proof. We just have got rid of the names, and it becomes, as a result, easier to read. And you can see if you had a longer proof like that, it would be a lot nicer to write it like this. And since this from this is an idiom that occurs very frequently, there's an abbreviation. Namely, you can just write then instead of from this. And then it becomes even more streamlined. You assume something, then you have something, then you show something, the final result. And since then, have, or then, show are also frequent idioms, you can again use an abbreviation, namely you can write hence, and that is short for then have, or you can write thus, which is short for then show, and then you get this even shorter proof down here. But these are just nice abbreviations. The essence is the one that you see here, where you explicitly see what you're referring to, namely this meaning the previous line, essentially. Then let's go back to the slides. So here just summarize the abbreviations that you saw on the slides. So I don't need to go through this one again. There's something else that's useful, namely an idiom called using. So instead of saying from something we prove, we can also turn things around. We say have or show some proposition using facts. So it's just a postfix rather than a prefix. You give the facts after the proof rather than giving the facts before the proof. Sorry, not after the proof, after the proposition that you're proving, but still before the proof. And this is just more or less the same as from facts, which you put after the proof. You can also put them after the proposition. You can also put them before the proposition, and it's just a different syntax for the same thing. And then there's also with, but I don't want to go into it. You may encounter it, and then you can go back to the slides. But this is quite frequently used here, the using afterwards rather than the from beforehand. Now, you can also write your lemmas in a more structured fashion, where you, for a start, don't need to give the types of variables inside the formula, but you can give the types beforehand. So you say fixes f, and then you give the type of f. So that's what you typically, if you write in prose, you would write let f be a function from a to a set. Then you can also explicitly give the assumptions rather than putting them, rather than proving some kind of arrow statement with a big arrow in the middle. You explicitly say, I assume something and I show something. So this is part of the statement that you're proving, and the statement that you're proving will now be an implication surjective of little f shows, implies false. Down here, if you see it, this is, oh, I can't highlight that. The bottom line is the one that will be the result of this proof here. This is not identical to what we proved earlier. Earlier we proved not surjective. Now we're proving surjective implies false. That's logically equivalent, but syntactically a different way of expressing the same thing. And I'm using now an implicational format because I wanted to demonstrate these structured proof statements, structured lemma statements, where you separate the assumptions from the conclusion. And then you do the proof as before, except that now there is, if you say shows false, if you just were to say proof without any dash here, there's a dash meaning don't try any automatic proof methods. I will tell you how to do the proof. If you were to leave out the dash, the system would say, I don't know, there is no default proof method for proving false, because you're trying to prove false, but I don't know how to prove false. There's no standard way of doing that. In contrast to if you give it a negated statement, it'll implicitly say, oh yeah, I know how to prove negated statements. You assume the unnegated statement and try to prove false. But with trying to prove false, there is no standard way of doing that. So here you give the minus, and it just says, don't do anything automatic. And you now know you don't need to assume surjective F inside the proof body. You have already assumed it as part of the statement that you're proving. And you've given it a name. You've called it little s. And so now you can do the second proof step right away, namely that there exists an A such that this so-called diagonal set, the set of all x such that x is not an element of f of x, equal to f of a, you can now prove that using S. So here is an example both of using and of referring to something that you have assumed as part of your statement, namely here the S. And so from the surjectivity of F, this statement follows using the same proof method as before. And then in one more step, you can show false using blast. So the only thing that, and then as a result, you get this implication surjective F implies false. So this is just an example for structured proof statements where you separate your assumptions from what you're trying to prove. And the difference is if you compare the proofs, if you compare the previous proof, what you see here, you have this text surjective of F twice in the proof. Once in the lemma statement up here, and once again as an assumption down there, surjective F. And that's something that one often tries to avoid, duplicating text, because it's bad for maintenance. If you try to change something later on, if you have the same piece of text twice, you have to change it twice. And B, it's also, it makes the text longer, and so it's not so nice to read. So here, using this method of assuming F, we don't need to write this surjective F twice, but we can just assume, we can just refer to it by name, by the name S that we've given it. So this is really part of the essence of structured proofs, that assumptions and intermediate facts can be named and can be referred to explicitly and selectively, because that's another problem that you have with these apply style proofs. If you just do things in apply style, then you always have this big set of assumptions hanging around, and if you try some automatic proof method on it, the automatic proof method may get stuck because there are too many assumptions. On the other hand, here you can name the assumptions, then you can say, oh, just use assumption 5 and 7 and then prove something from it, and then it'll be much more goal-directed and the system will be less confused. The automation will be less confused. And this is the general form of the structured lemma statements, but yeah, I don't need to go through that here. So this was the initial introduction to the system using a specific example, and now we will go through various proof patterns. And I really recommend that when you are in a situation you want to prove something, remember what is the suitable proof pattern for this situation. So, first, case distinction. And so there's the case distinction where you're trying to do a proof by cases on some proposition, and that's what we see over here on the left. You're trying to show or have. I mean, both of these work. This pattern works no matter if there's a show or a have here. So you're trying to prove some R, and then you say, I'm doing a proof by cases. And then the proof blocks that follow it have to look like this. In the first block, you assume some P, and now you can decide what you're doing your case distinction on, and you have to show R. And in the next proof block, so there are two proof blocks separated by this next statement, and in the next statement, in the next proof, you're assuming the negation of P, and you again show R. So here you're basically doing a case distinction on P. And using this pattern, you don't have to give the P explicitly. You can give it, you don't have to give it right there when you do your proof. You can give it in the subproofs, in the two subproofs, once you give P and once you give not P. There's an alternative proof by cases. So this one is by cases on some Boolean formula and assuming once the Boolean formula and once assuming its negation. Another form of case distinction is if you know a disjunction between two formulas. So if you have proved that P or Q is true, and then from this fact here, you want to show R. And now it's very important that you have this then here. This then means that you're piping the disjunction P or Q into the next proof. And the next proof will say, oh, there's an incoming fact. I should take a look at that and see if it's something that is meaningful. And this proof here now will look at this OR and will say, oh, there's an OR coming in. So that means I have to do a case distinction on P or Q. And so in one half you assume P, and in the other half you assume Q. So it's basically the same proof as over here, but you've just used the, over here you can see this, the left one, as a special case where you're using the fact that P or not P, and here is the general case where you could have any or P or Q. And then you have this binary case distinction. If you want to distinguish more cases than just two, I'm not covering that on the slides, it's a bit more verbose. If it ever comes up, it'll be on the exercise or tutorial sheet. But these are the two important ones for binary case distinctions, either formula and its negation or formula or formula. And it's really this pattern that you then have to write where this then is, if you leave out the then the show R will not know about the case distinction here and will not accept your proof. So it's really the or and the then that allow you to write this proof pattern. Contradiction. If you want to prove something by contradiction, there's the situation where the thing that you're trying to prove is already negated. And this situation we have seen with Cantor's theorem. You're trying to show the negation of something. Well, just to prove, then it'll automatically allow you to assume the unnegated formula, and then you'll have to show false. This is a special case. The general case is that this formula is not necessarily negated, and then you have to do it like this. You have to explicitly, you show some arbitrary P, and then you explicitly say, prove this by rule C contra, which stands for classical contradiction. This is the general case. Over here on the left, we saw the specific case where what you're trying to prove is already negated, and the special case on the left is simpler because if you use the case on the situation on the right, you wouldn't be. If P is already negated, and then you have to assume a doubly negated formula, which just makes two things complicated, whereas here on the left, you don't assume any negation. So it's much simpler to use the pattern on the left if you have something negative that you're trying to prove. If the thing that you're trying to prove is not negative, well, then you have to go through this explicit appealing to the rule classical contradiction. So this is really a rule in the system that supports this proof pattern. This is what you do if you want to prove an if and only if, or one way of proving an if and only if. If you just say proof without anything, then the system will again look at what you're trying to prove and say, oh, it's an if and only if. So what we should be doing is we should prove both directions. So you're allowed in one direction to assume the left-hand side, and then you show the right-hand side. In the other direction, the converse, you assume the right-hand side and show the left-hand side. Yes?
How would you now prove one direction by contradiction, for example?
Well, let's assume the first one here is you want to prove by contradiction, then you simply use exactly this proof pattern here. So you write this proof QED block in here after the show. So this ... is the proof, is the open proof, the missing proof. Now come the quantifiers. They deserve a little bit more attention. So how do we prove something that is universally quantified? And that follows the standard textbook style that you learn in any introductory math course. It will say, well, if you try to prove a universally quantified statement, just pick an arbitrary value for that variable, and that's what this fixed x means. You introduce a local fixed variable, and then you show your proposition for that fixed variable. Yes?
Is that really required? Because if P is defined, and we just give the proposition as P of x, then x should be a fixed local variable in the theorem, right?
Yeah, but see, that's the difference. We're not doing things implicitly, we have to spell things out explicitly. If you look into an introductory math text that tells you about proof methods, it will say you assume some fixed value for the universally quantified variable, and then you show the proposition inside. And you really have to spell that out in full detail here.
Okay, so there is a difference between the theorem P of x and for all x P of x.
Yes. It's a syntactic difference. You can, from one, derive the other. And it's really the question of, so that's why you actually leave out the quantifiers as much as you can. You try to write not all the universal quantifiers in front. If you're trying to prove, if you prove, for example, x squared is greater x, it's easier to not say for all x, x squared is greater than x. You just say x squared is greater than x. And then implicitly there's a universal quantifier, except that you've already got rid of it. Here there is an explicit universal quantifier, and you have to make this step and get rid of it. How about the existential quantifier? If you're trying to prove an existential statement, then the standard proof method of doing it, so if you just say proof here, the system will assume, oh, this is what you're trying to do. You're trying to prove an existential statement. What's the way to do it? Well, you eventually, in that proof block, show that existentially quantified statement, and you give an explicit witness, some term for which you can show that P is true, 5, 42, whatever. And the existential quantifier has disappeared, but now you have to come up with this term and prove that P is satisfied by that term. So these are the so-called introduction rules because they show you how to prove a statement that introduces the universal quantifier and introduces the existential quantifier. This may be confusing because they seem to disappear, but we're using the rules backwards. So this is the conclusion, and inside we're proving something from which this conclusion follows. That's why it's called an introduction rule. Now, of course, that's the converse. If we, yeah, right. No. I was going on to the next slide. So,
from looking at the syntax of universal quantification,
yes.
So it looks more or less like the existential one. So there must be some internal which enumerates of the x by the bonus set, right?
Hang on. You're saying the universal is existential? No, you must have said something else.
It says fixed x, right?
Yes.
So in formal logic, to prove it, you have to say for all. So you have to enumerate all the elements in the set, and then show that for all of them the predicate holds. Right?
Yes.
So,
but you can't enumerate it because it will typically be an infinite set. So therefore, you just pick some arbitrary but fixed value for it, and then you show if it worked for that arbitrary value, therefore it must work for every value.
So fix basically there's some kind of additional meaning to fix, which means that it is anything.
Yes, so it's a new name. That the fact that it's new is just guaranteed by the system, because if there is another x somewhere out there, it will just shadow that other x, and it will be really a new x. So that's why you, just by scoping, you know it's something new, and that's all you need to know. If it's something new, then it's arbitrary. You don't know which one you've got. And so this, that's the, in some sense, that's the beauty of logic, that all you need to do in order to prove a universal quantified formula is you pick some new name and you prove it for that name. And then you know you've proved it for everything, because the name was new. And that's exactly what the fix does. Introduce some new local name.
This is hard to pick from the syntax. So.
Pardon?
This is hard to judge from the syntax, because fix suggests that you pick one and make it constant. You assign a fixed value.
Yes, you are fixing the value, except you don't know what it is. You're fixing some arbitrary value. That's why you're not saying fix x to be 5, but you're saying fix x.
Sure.
And since you don't know what you just said it's fixed, you can't change it within that block. That means it'll work for everything, and you're not making any assumptions on x other than it's new.
Okay.
Yes.
Is there a difference between fix and fixers?
Yes, but only where they occur. So fix is inside a proof, and fixes is in this structured lemma statement. So if you look, we were here as the general. So this is here. This occurs in the statement of a lemma, and again here it's called assumes and shows, and down here it's called show and assume and fix. So it depends on where in the proof, whether you're in a proof or whether you're in a statement. So let me move on to the elimination rules. What do you do? What can you conclude from an existential or a universal statement? And the elimination rule for an existential, that's something where there's really an explicit language element in ISA, and this is called obtain. And so this is how it works. If you, in the simplest case, you just have an existential statement, and from that you want to continue. And when you write proof in mathematics, what happens, and often people don't even explain this at all, even in introductory courses, that on one line you have an existentially quantified statement, and on the next line you've suddenly given yourself, you've just suddenly dropped the existential quantifier. So, like here, you write there exists an A such that A, I don't know, A plus B equals C, and A and B and C are something further up in your proof. And then in the next line you write, oh, this implies that A is C minus B. And suddenly you've gotten rid of the existential quantifier, you just treat the A as if it had always been there. Why is that okay? That's here we do it explicitly. We have this obtain statement. We say, okay, we have an existentially quantified statement. There exists some x. Well, then please give me some x that has this property, namely that p of x is true. And this line basically has removed the existential quantifier, but you really did this explicitly as a proof step. And you, strictly speaking, you have to do this explicitly. And in the rest of the proof, x is a fixed local variable. So in fact, in this obtain, there is a fix hidden in there, which you don't see, but and from now on you can treat this x as if it was a variable that you can, I mean, because here, at this point, the a is really a local variable, and it doesn't matter whether you call it a or x or u, the statement is always the same. I mean, the logical content is the same. But here you suddenly make use of a specific name after that. You will always call it A, and so therefore you've basically you've done something like going into the scope of a locally quantified thing, and that's what we're doing here. Explicitly, we're saying, oh, please then give me an X, which I can now use for the rest of the proof, and give me the assumption that P of X is true. Yeah.
So will this always work by class?
Yes. This step is so trivial that, in fact, yeah, at last is already overkill for it. Yeah. And it will work not just for one, it will work for any number of existential quantifiers. Then you would say, if you have here exists x, y, z, then you would say, then obtain x, y, z, where P of x, y, z. And, yeah, that's what I just said. Here's an obtain example. Right, because earlier on we had this maybe not so clear step in the proof of Cantor's theorem, where we've got this far that there exists a little a such that this diagonal set is f of a. And now I claimed earlier on, from here it's logically easy to get to a contradiction. And now we will look at this step from here to false in more detail. Because now we say, okay, now please give me a little a that has this property. So you then, and the then of course is important because you're using the previous statement to obtain this little a. Obtain a where, and now you just copy this equality here bypassed. So maybe now it's easier to see that this is contradictory because we are comparing two sets here. Well, if two sets are the same, then some element is in one set if and only if it's in the other set. And now the element in question that we're going to look at is the little a itself. And so we're now deriving from this equality, the equality that little a is in the left-hand side if and only if little a is in the right-hand side. But what does it mean that little a is in the left-hand side? It means that little a is not an element of f of a. What does it mean that little a is on the right-hand side? It means that little a is an element of f of a. Well, that is clearly contradictory. And so from here to here, it's just a very simple set theoretic reasoning that says if two sets are equal, then an element is in one set if and only if it's in the other set, plus the reasoning that if an element is in a set comprehension, it must satisfy the predicate in that set comprehension, and that's what we've written here. And now, thus false by blast is really not surprising anymore. And so this is something whenever you in a deduction get to a point where you have an existentially quantified statement, then most likely you will have to continue by getting yourself a name for that variable and then continuing with the unquantified statement and deriving something from it. I think it's, oh yeah, this is the last proof pattern, what to do with sets and subsets. How do we prove that one set is equal to another? So here, some of these things were just done by the automation, but sometimes you will have to do these things explicitly because the automation can't cope with the whole proof, and so you have to go into subproofs. So maybe, for example, you couldn't automatically prove that set A is equal to set B, so then you say, okay, let's do two subproofs. And if you just say proof here, the system will automatically say, oh, you're trying to prove equality of two sets. So then you'll have to show that one set is contained in the other and conversely. And maybe these proofs are simpler than the equality proof because the equality proof it's just overwhelming the system. But maybe these two proofs can be done automatically. Now maybe the proof A subset or equal B couldn't be done automatically, but then you can again prove it explicitly. How do you show that one set is a subset of another one? Well, you fix an arbitrary element, you assume the element is in the left-hand set, and you show that the element is then also in the right-hand set. So this is how you get from a maybe more complicated statement to a simpler and simpler statement by using these proof patterns to reduce your statement to simpler ones where you can assume certain things and show other things. And now I think it's time to actually do a little exercise with you using the system and using these rules that you've seen, or rather using the proof patterns that correspond to these quantifiers. You may wonder, so here we have a pattern what to do, how to prove a universally quantified statement, how to prove an existentially quantified statement. We have a proof pattern how to prove something from an existentially quantified statement, but I didn't write down any proof pattern how to prove something from a universally quantified statement. And the reason is very simple. If you have, maybe you've just proved have for all x, p of x, and now you want to prove p of 5. That's so trivial that no proof pattern is necessary for it. You can just say hence, meaning from this half, p of 5 by blast. So this step of instantiating a universal quantifier with a specific value is not something that requires anything in the language. It's just the automation does that automatically. Because, yeah, it's really not a big deal. There we are. Now let's go over to an exercise. Here are just the proof patterns again that you've seen on the slides. Yep. So this is, maybe I'll make it even bigger, the interactive exercise that I would like to go through with you. So what are we trying to prove here? That there exists, that from the assumption that there exists an x such that for all y, p of xy, we can prove that for all y there exists an x such that p of xy. So if you find the statement confusing, you can think of P as loves. So Pxy means X loves Y. Then the first statement means there exists somebody who loves everybody. And the second statement means everybody has somebody who loves him. And that's clearly an implication. If there's one person who loves everybody, then everybody is loved by somebody. In fact, that's a weaker statement because the first one says there's one that's in relationship to everybody. The second statement just says everybody is related to somebody, but it doesn't have to be the same person. So let's try and prove this. So I'll start out and then you'll have to help me. So hopefully this is the proof and we'll have to put something in the middle. So what should we be doing here? Yeah?
Can you also show the proof state?
Yes. No. I want us to, because you don't need to see the proof state, the proof text should be completely self-explanatory. But you'll have to figure out what to write now. Yes? You can do that, but it's a bit too premature. It will do that as the next step. But we've written now proof without anything. So that means the system will do something by default. What do you think it would do by default?
I think the shows syntax is used. I'm not sure what that is.
This is from the structured proof statement, where you have an assumption that you have and a shows. So where you separate the assumption from the conclusion.
Does it ask
Sorry, a witness for which? For the conclusion? But we haven't even, I mean, the conclusion is that it still has a universal quantifier, so you're jumping ahead. You can't get at the existential before you haven't get rid of the universal.
So fix y.
Yep. And in order not to, I will call it B, because otherwise everything is called X and Y and it's terribly confusing. Fix B. And what do we have to show? Here we will not change the name. We will leave the X there to see that. We could change the name here as well, but and what do we put instead of the Y? The B. Yep. So this corresponds directly to the first rule that you see there. You're trying to show universal statement, and so you fix some variable for the universally quantified variable, and then you show the thing inside the universal statement. So here we are. Now, what we will do is, between the fix and the show, we will now do what you suggested. We will obtain something, namely from the assumption here. So we can write from assumptions, and there is only one assumption. That's what will be given. Obtain, and now we call this thing A rather than X, just for variety, where what is the property? Well, the thing inside this one here. And this is the A. And just by blast. And we give it a name because we may want to refer to it later. So let's give it a name. You can also use star as a name. So how do we prove this thing here? Well, let's just write proof and QED. And you tell me what you have to prove inside. So we'll have to have some show, but what do we need to show? Go back to the slides. It's the thing down here. How do we prove an existential statement? So we go back. So what do we write here? Yeah? P of A, B. So you have chosen A to be the witness for the X, and that's perfectly fine. How do we prove this? Where does it follow? From what does it follow? From star, right. And then you just say by blast. Because that is the example I had here. You're using a universally quantified statement for all y, P of AY, and you're showing a specific instance. That's just a trivial blast step. And that's it. That's the full proof. And here you see in this single proof all the 4 patterns of using the quantifiers, either proving a quantified statement or proving something from a quantified statement. Then let's go back to the slides. And for this course, something else is important, not just quantifiers and or, but also equations and inequations. And this is what I want to introduce next, how to write chains of inequations. So this is what textbook proofs typically look like. If you have a more complicated derivation, and then it'll be split up into a sequence of lines, typically saying some term equals some term t2, and then with some and then afterwards the justification for that, because the logarithm is whatever. And then you can write these chains, and you don't repeat the previous term, you just write in the next line equals and then the next term. And then you keep justifying on the right why the transformation from the previous line to this line is correct by some well-known mathematical fact. And that's exactly the pattern that we will also follow, except with minor syntactic details, minor syntactic changes. So this is what it looks like in Isabel. So you start out with just a normal half, and then afterwards you just have a proof, as we used to. And then if it's a chain of things that continues from the previous half, then you write also half, and then you still have to write an equality, but you don't have to repeat the term t2. You can just write dot, 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 really literally dot, dot, dot. And then equals, and then the term t3. And then again another proof that proves this equality. And then you continue, keep going until you've reached the last term, and you've shown that the penultimate term is equal to the last term by some proof. But then you still have to explicitly state the consequence of this long chain. Namely, the consequence is that t1 is equal to tn. And so you explicitly say with the keyword finally, which takes the result, combines the result of these previous things and feeds it into the next statement. Namely, you show t1 equals tn. And here the proof is simply dot. And dot is a proof method that you can use in general. It just says by assumption. So dot is just sort by assumption. So this means the result of all of these things that are gathered together by finally had better be exactly this equality. So if this last step doesn't work, then you've somehow T1 or Tn is not exactly what you've... so this T1 is not equal to this T1, and this Tn is not equal to this Tn. You've made some typo, and then it'll complain about the last step. Otherwise, the last step will be a trivial one, because you're just repeating the terms T1 and Tn. And then, of course, here you really have the equality that you want, and you can then continue from that, or that is the thing that you wanted to prove in the first place. And really, dot, dot, dot is literally 3 dots. So it's part of the concrete syntax of the system. And you can use equations and inequations, but only in one direction, please. So only less than or equal or less. You can't write it in greater than style. If you try to do that, the system will completely will not accept your proof. You really have to start with the smallest term and get larger and larger, and you have to transform. You just have to do your proof steps in the other direction. If you wanted to go from the larger, you have to rearrange the proof. And here's a simple example. I mean, it's not really an example, it's a generic example where you first prove T1 is less than T2, and then you prove that the previous one, namely T2 is equal to T3, and then you keep on going using equality less than or equal or less than, and eventually you get to some Tn, and then of course your finally show must be a less than sign, because in this sequence you had a less than sign, so as the whole sequence it must be less than. So the result that comes out of here, of the whole proof block, and that is gathered together by finally, is really this one inequation T1 is less than Tn. Of course, if everything is less than or equal, then in the end you can say less than or equal here. But you really have to, you can't, for example, if you were to write less than or equal, that would also be true, but it wouldn't follow by dot. So you then have to have another step to turn the less than or equal into a less than, the less than into a less than or equal, or you better use less than only in this chain if you only want less than or equal at the end. This is just a look inside how this is to be interpreted, but let's ignore that. So let's look at an example and an exercise for this. And actually, let's stay with this for a moment, because so far I haven't shown you the output window because I didn't want to give you any hints, but the output window does contain hints. Although the proof is readable in itself, if you open the output window, you will actually get some more information. Namely, if you... that was too much. So this is the exercise that we started with, that was on the previous slide. And now let's see what the output window shows us when we look at some specific points. So for example, if we look at after the proof, and then the output window will actually show us what we have to prove at that point. Now the big AND, the meta universal quantifier, it says, okay, you have your local y, and what you really have to prove is this formula here. And that corresponds to what you've written down here. Here you've written down, we have to show that it exists in X such that P of XB. But note that we have used different names. The system does not follow your naming convention. It'll follow its own naming convention. So the fix B here has no influence on it. But you can always, when you go after a proof, you can always see what is it now thinking I should be showing. And here, after this show of an existential, down here you see, oh, I have to prove P of something and B. So it shows you that you have to provide some witness for the question mark X. And this is what we are doing here when we show P of AB. So if you look after a show, you'll see what there is to show. And also, if you say, for example, after the from assumptions, it'll say explicitly show you what is this assumption. So here it says picking this and shows you what this is. So if you have a big proof text, it can be quite helpful because you may not, it may be a page further up what the assumptions are, but if you just click on it, then you say, oh yes, the assumptions were, and then it shows you down in the output window what it's picking. So picking means I'm using something for the assumptions. Same here when you say from star, it'll again say picking this, and this is now the start statement up here. So this just to explain what the link is between the output window and the theory buffer. So the output window does give you some helpful information about what you're supposed to prove at that point. But now let's move on from these. Move on to the inequations, and here is the example. Let me just, yeah. So we want to show that 0, the real 0, so we're fixing on real numbers here. For that one, the statement is true that x squared plus y squared minus 2xy is greater than 0. Yeah. And here's an example of such a chain. So you start out with having with proving that 0 is greater than x squared minus y squared. So this is the key to it. You realize that this is just another way of writing x minus y squared. And now you're giving the proof with x minus y squared as the middle term. So you first show that 0 is greater lesser or equal x minus y squared, which is simply done by simp, because simp has a rule that for the real numbers, the square of anything is greater or equal 0. And then you say also have, and now the dot, dot, dot refers to the previous term on the right-hand side, namely x minus 1 squared. And you can actually see that if you say also have, you go there. What is it asking me to show now? If you look at the output window clearly shows you the left-hand side of the equality where you have just written dot, dot, dot. The system has filled in the dot, dot, dot and has put in x minus y squared. So down in the output buffer, you will see the full text. Up here, you see the abbreviated text with the dot, dot, dot. And how do we prove this? Well, here it's really an equality. It's just a question of multiplying this square out. And this is what the algebra simps does. I mentioned it by the proof in the proof automation section. Algebra simps has rules for multiplying out multiplications which contain additions. But you also need to get rid of the square. So here the x squared is not simp will not, if you just say simp and then there's a term with x squared, it'll just keep that square. But if you also add this funny thing here, numeral EQ suc, that was the thing I alerted you to, that will turn every numeral into a successor term. And once it's a successor term, this thing here can be evaluated. It will be evaluated to x minus y times x minus y. And similarly here, but here it's not necessary. So this x squared will become x times x, and the y squared will become y times y. So if you didn't do that, so let's just remove this, then you will see nothing works, and you can see down here it has rearranged things a little bit, but so this is what it's trying to prove here, but the x minus 1 y squared hasn't been multiplied out, and so this is what only happens if I replace the to the square by successor of 0. Then it'll the evaluation mechanism for exponentiation will kick in and it'll multiply things out. Conversely, if I put this in, but I don't put in algebra simps, then you see it won't prove it either. And here, down here, that's now more readable. That's exactly the left and the right-hand side. It hasn't changed them, but it has turned the square into a multiplication, but it hasn't multiplied things out. So this is what the second set of rewrite rules does. The algebra simps, and now it's multiplied everything out, and now everything came out. And then you have your last statement, which simply gathers together the previous steps, and then you say, okay, finally, as a result of these two steps, we can prove now that 0 is less than or equal to x squared plus y squared minus 2xy. And that is just dot. And you can also, if you go after the finally or on the finally, it'll say, picking this, so it got this out of the previous calculations, and this is exactly what you're trying to prove, and therefore this by assumption dot will successfully prove it. So this is one example. Now we'll do a little exercise. Oops. That's not quite what I wanted. Why is that in there? Yeah, okay, it is what I wanted. So we now want to prove that x minus y squared is less or equal x squared minus y squared, assuming x and y are real, and x is greater or equal y, and y is greater 0. And I have started with the first line in my proof. So I do proof minus because I don't want to have anything automatically to happen. I just really want to prove this statement. And so I start out with this line, And this line, I've already given you the proof. I've multiplied out the x minus y squared, and I got x squared minus y plus y squared minus 2xy. But where we want to get is this one, x squared minus y squared, as a bigger term. So we have to start some sequence of equations and inequations. So what should we be doing continuing on from this term here? Using the assumptions, obviously. Any suggestions what we could do? Yeah.
Well, we have the assumption that x is greater than y.
Yep.
So 2 times x times y is greater than y squared.
Yes. Yes, greater or equal. Yeah. Yes. And so this is what we're going to do. We're going to restate this right-hand side, but with the y replaced by the x at the very end. So we'll write also have, and now comes dot, dot, dot for the previous term, equals. Now I've just copied the previous term, but now we want to replace the y by an x. And we're claiming this follows by which assumption? Oh, it's not equal. Sorry. My mistake. Greater or equal. Yeah. So which assumption should we use? Pardon?
They don't have lengths.
First one is fine. Using assumptions 1. Yep. By simp. Now that didn't work, so let's write apply simp, and then we see what is left over. Couldn't prove that. Why not? Yep.
Probably we need
We need what?
maybe we need algebras.
No, we may need it, but that's not the key. We could, let's just see what happens. Yeah, it's a perfectly reasonable assumption, a perfectly reasonable idea. So let's just copy this thing here. And we don't want to get rid of any numerals, so let's just do this one. Didn't make any difference. Yeah?
I don't think the statement is true.
The statement is true, but you need to say a bit more. Or rather, this particular, if you just look at this part, indeed that's not true.
Yeah, we also need y greater than 0.
Yes. So this implication, if you look at it, is not true, for example, if y is 0 or if y is negative. So we need both assumptions. And so we don't just focus on one, we need both. And then, so it says down here using this, so it's showing us what it's using. And then if you now apply simp, maybe
by blast is sufficient. Maybe the simplification is misleading.
But that doesn't follow. I mean, if y is equal equal x,
I think we swapped them.
that is quite possible. So I've
Maybe 2 times y times y. Yeah.
but then it becomes smaller. I don't understand this.
No,
no, x is greater or equal than y, and you replace a negative x, y by x.
No, not, y is not negative. Y is greater than 0.
You in the step from the first equality to the inequality.
Because it's minus. Yes, yes, yes. My mistake. Okay, but you did notice eventually. It wasn't intentional, but I think it was a nice exercise. It should have been y. And now let's see. And now it says no subgoals down there. And now we can even try if we do need algebra sims. Maybe we don't. In this case, we don't. But it's not, I mean, it's in many cases you do need it. And then we could just write by. Okay. So how do we continue from there?
We have to somehow subtract both sides, so we can reduce 1 to something 0 smaller than.
No, you can just manipulate the previous term. And you tell me what you want there. Yeah?
Smaller than x squared minus y. Oh, no. Yes, it's smaller than x squared minus y.
Yes, and it's not even smaller. It's
Smaller.
it's equal.
Well, this is small equal.
It should be enough, but since I think it's better to be more precise if you can. And so it's equal to x squared minus y squared, right? Yeah. Which is what we have to prove. So it had. So how do we prove this? Yes. So it's leaving us some subgoal. Y squared is y equals y times y. So no.
Yeah, the numerals are getting in the way.
Yes. So we still have to convert the exponent 2 into a successor term, and only then will it expand the power operator, because the power operator is defined by a recursion on the successors, and there is no successor in the exponent. This actually makes a lot of sense. You wouldn't want, if you have x to the 17, the system to automatically expand this. That would cause a great mess. So it's quite nice that it doesn't do that, and you have to explicitly ask it to do it. But you could just, I mean, typically, if the statement like by, sim, add, blah, blah is already around, I could just have copied this line and used it and see if it worked. And if it works, then you're happy. You don't need to sort of incrementally construct it. But, yeah. Yes, then it says no subgoals, and then you can make by. And then we just have to add this finally show and the dot. Yeah, that's it. And I think that pretty much brings us to the end of the lecture. Let me see if there's, we still have some 5 minutes, so we should use the time. Yes, let's introduce you to a few of the gadgets for making proofs shorter. And the first one is pattern matching and quotations. So this is aimed at having to write less text by avoiding repetition. And here is a simple example. If you, well, I should have first shown you the original text, and then, hang on, where are we? Here, right. This is the text. If you look at this proof pattern for the if and only if, then what you'll notice that there are now 3 copies of P and 3 copies of Q in that. And if those are big formulas, it's rather painful to have to repeat them so many times. So what we'll do is, at the point where you put the show, you introduce abbreviations, namely names for the left and the right-hand side, and then you can use those names rather than the full formula inside the proof. And so this is what's going to happen here. Here you explicitly, after the statement of your proposition that you're trying to prove, you say, please match this proposition with the proposition question mark L if and only if question mark R. Remember, these question mark variables are unification variables, so you're going to unify the pattern on the right with the formula on the left. And as a result, of course, question mark L will now stand for formula 1, and question mark R will stand for formula 2. And then you can write down this proof pattern, which looks like the proof pattern we had, but now L is really just, question mark L is just 2 characters rather than you don't have to write the full formula 1 there. And so now it becomes much more condensed and free of duplications. So if you now have to maintain that proof and you suddenly decide, I need to change formula 1 into formula 1 prime, then you just need to change formula 1, but the pattern L will propagate that change into the proof blocks, into the 2 proof blocks. Of course, if you change the formula, probably you'll have to change those proofs as well, but at least you don't have to change the text of the formula 3 times. This is a specific instance of this, is something called thesis, and that is useful when you're trying to have a subproof where you again show the same thing as in the full proof. That happens from time to time. If you have show formula and then you don't do anything, you just say proof minus, don't change the formula that you're trying to prove, and then down here you say show thesis, then this thesis will refer again to that formula up there. So essentially, every show introduces implicitly one of these pattern matching constructs and pattern matches the formula that you're trying to show with thesis. So this is really, thesis is the last show that I was attempting. That is, it's short for that. And so, in fact, where is an example of using this? If we go back to our example, where can I use thesis? It may not be obvious here from what I showed you. I can use thesis here. Because it was implicitly in this shows line, the green shows line, there the thesis was implicitly matched to the thing that you're trying to prove in this block, and we're still trying to prove that same thing, and therefore I can just write thesis. And so thesis always, I'm now proving what was originally my goal when I started this proof. So these are just abbreviations. In some sense, you don't need them, but they are handy to have. And so every show and shows also implicitly defines thesis. And here is how you can explicitly introduce an abbreviation. So if there's some big term that maybe occurs repeatedly, or even if it doesn't occur repeatedly, if you just want to bring it out, then you can, in the middle of a proof, you can say let question mark and then some name equal and then some big term, and this will just be an abbreviation for that big term, and then you can use that question mark T in further statements and avoid having to write the big term out in full. So this is something, for example, if you want to produce a witness for something, often the witness is some complicated, interesting term, and then it's nice to bring that out, and then you can just say later have some proposition of witness rather than having to expand that term in place. And finally, that's what I'll close with today, is quoting facts by value. What does that mean? So this is the conventional way of doing it that we've seen so far. You have some proved something like x is greater than 0, then you give it a name, let's call it x0, the name, and then further down you say from x0, blah, blah. And now it's painful to have to invent all of these names, and in particular a name a name for something that's already a very short fact. Wouldn't it be nice if we could say from the fact that x is greater than 0, rather than having to invent a name for it? Which, of course, only is a good idea if it's a short proposition. If it's a long proposition, you don't want to refer to that whole text again. But you can do that, and this is the way to do it. Rather than invent a name, you just prove the proposition, and then later on you refer to it by value. Namely, you put, unfortunately my battery is dying, you put these back quotes or back ticks around the formula. The fact that I've not put any spaces there, I've just written x greater 0 has no relevance. So you take that formula, put back quotes around it, and then that formula will be inserted there. Oops. Yeah. And these back quotes are just a hint to the system. This is not the name of something, but it's the value of something. Namely, the proposition with that value. And that, I think, finishes the lecture very nicely for today. And yeah, we don't need any demo of this. I think they are self-explanatory, these pattern matching things. Any last questions? Well, in that case, have a good weekend and see you again next Friday. And